Let's see how you've done with this example. I notice that we have initial concentration of A, initial concentration of B, and an overall rate. I start looking through the data table to find, do I see a place where one of the reactants is held constant while the other changes? And that's the place I go to first. I'd like to hold one concentration constant so that it's not influencing the rate. Well, I notice in trial 2 to trial 3, the concentration of A is indeed held constant. Therefore, it will not be influencing the rate. And I notice that the concentration of B has indeed doubled. I can prove that by showing in trial 3, the concentration is 0.80. The concentration in trial 2 is 0.40. That indeed is doubled. Well, what happens to the rate? Again, comparing the rate in molarity per seconds of 14460 compared to 3600. That's probably mental math for some of you, but I'm going to check that out. 14460 set over 3600 gives me a value of 4. When I doubled the concentration, the reaction rate quadrupled. In terms of respect to that order, 2 squared is 4. This looks like a second order with respect to B. So here's what we know so far. Rate is equal to K times the concentration of A, yet to be determined, times the concentration of B, we just determined to be a second order overall. We don't know yet the concentration of A's influence. Interestingly enough, concentration B is never held constant. So we'll have to consider that when we look at how A is influencing. So we have a couple of ideas. We can compare trial 1 to 2, which would have doubled. And that might be easier than comparing trial 1 to 3, where we make it 4 times as much. You can pick either one. I think it might be a little easier if I consider trial 1 to 2, now knowing that the influence of the rate is second order with respect to B. So here's what we know. From trial 2, the rate is going at 3600. In trial 1, the rate is going 300. Let's find the factor at which it increased its speed. So 3 into 36. So 3600 divided by 300 shows us an influence of 12. The reaction is now going 12 times as fast. Alrighty. But we also know both reactants are influencing that speed. But we can factor out knowing that B is second order. Here's what I mean. When I look at trial 1 to trial 2, concentration of B is 0.4 to 0.2, it doubled. We know that this is a second order, so that just by doubling the concentration of B, the influence of this rate from that reactant is a second order power, it's 4. Let's factor out. It was going 12 times as fast, but a factor of 4 is coming from the influence of reactant B. Let's factor that out and find what's left. That tells us that 12 divided by 4, the influence of that reactant B factored out, leaves us a factor of 3 that must come from the reactant A. From the first trial to the second trial, the concentration of A was tripled. The rate is going 3 times as fast. Tripling the concentration and the rate follows directly makes it a first order with respect to A. I started with comparing trial 2 to 3 because I held one of the reactants constant. That allowed me to factor out and find a second order with respect to B. But because B was never held constant, I had to factor out its influence from trial 1 to trial 2. Notice how from 1 to 2 the rate is going 12 times fast. From that 12 times factor, Two things are influencing it. We determined the influence of B, factored out that 4, that's 2 squared. Tripling the concentration of A left an influence of a first order overall. So we read this as rate is equal to K times the concentration of A to the first power. B is to the second order, its third power overall. To find K, we just pick a trial. I always pick trial 1, but for no other reason than it's written first. Its rate is 300 molarity per second. That's rate. It's set equal to K, what we're solving for, times the concentration of A raised to the first power, times the concentration of B squared to the second power. Let's solve for K and include the units. 300 divided by 0.1 to the first power divided by 0.2 squared gives us a K constant of 75,000. And let's consider the units for that number. Remember, our unit is molarity raised to the negative, well, it's 1 minus the overall order. Remember from up above, 1 minus the total order? Well, the total order here was 3. 1 minus 3 gives us a factor of -2. So molarity to the -2, and remember that time in this data table is seconds, so it would be per second, or second raised to the -1. The K constant has a value of 75,000. The unit on K, molarity -2, second -1. That's the same as writing 1 over molarity times second. We shorten that by putting molarity -2, second -1. It's seconds in this example because that's what the data table gave us. Up at the top here it was per minute. So I'm just kind of matching that time unit to what was provided in the table. Pause here and stare down the next data table. It sets up the problem here, but the data table is actually on the next page. Try it on your own first, then start up the video.